The speaker is also today Ilya Pavlyukevich. I butchered your name again, sorry. I have to ask it better today. And he's going to talk about, again, interesting stuff about stochastic differential.
Yeah, thank you very much. So I don't want to bother you with many talks, but I think this is an interesting part because people do simulations, and I ask several questions, and it's about a very simple equation. So, but well, it will be more difficult. But so the first one, and actually, so the title is how to simulate, and you can ask. So I wanted to make the title, by the way, how to simulate, because we believed that everything is known, and you don't have to do anything, but it is not true. So I just start with an illustrative example, very simple, one-dimensional, and then at the end I will show general setting and multidimensional, but all the problems which we have, so they will be illustrated here. So scalar stochastic differential equation, x dot is minus x to 9 plus z dot. So x to 9 is a drift, or minus x to 9. It's exactly so what you have with 3. So this is a gradient. You can think of this as a minus gradient of the steep potential, x to 1, so x to 10. But you can put 100 here, so that's not a question. So this is one difficulty, of course, because this is not global ellipses. It is dissipative, but it's not global ellipses. And if you do some numerics, you run into problems. I will show you in a minute. The second point here is Z. So Z is a Cauchy process. So those who know, so this Cauchy process is a good process, actually. It's a process with independent stationary increments, but it is not integrable. It has very heavy tails. So the marginal distribution is a Cauchy distribution. The mean value does not exist, and the variance does not exist. So this means the question is, you have here two problems which meet. So very steep drift, and very heavy tails. And then we want to simulate this. And the question is, of course, what do you mean by simulate or solve numerically? So what do you mean? So of course you can speak about paths, but we wanted, and this was our question. So we wanted to calculate some physical values, like the mean value, the variance, maybe the higher moments if they exist. But the main question was, so we wanted to calculate the second moment, this is the energy, numerically. So what is the problem? So, okay, so, yes, the problem is the Cauchy process. It looks like this for those who does not remember. So it fluctuates, it consists of jumps. The jumps are everywhere. And from time to time, you have very, very big jumps. So here is the jump of the order 10. But it's not seldom that you get jumps of the order 100, 1,000, 10,000, just you see it immediately. So you integrate just and they appear. And these are the absolute moments. This is the formula in the symmetric case you can calculate. So the moments up to order 1 exist and are finite. So the moments larger than 1, including 1, do not exist. So they're infinite. So now you can ask the general question before you start simulating. What can we expect from this equation at all? So do they exist, the moments? So, and people very often argue, well, the moments of the solution of x do not exist for orders larger than 1, because it's a very simple argument, so which is wrong. You say, well, you have dx here, so this is the integral, well, more or less finite, and here is the z, if you write it in the integral form. Let's take expected values. Have expected values of x or some power. Expected value of that and expected value of that. So here the expectation does not exist for the power larger than 1, so this means everything breaks down. This is not true. Actually, so in this case, we have finite moments up to order 9. And this can be proven, so physicists do this by many ways, and but to be honest, so the most general result on this subject is my paper with Alexei Kulik from Wrocław University. So we did it, so the motivation was quite different. So we wanted to study slow-fast system, and we did it in a semi-martingale setting. But just, I tell you, so you see, so imagine that this is a solution to our SDE. This is a drift part, so this is a continuous martingale part. Brownian motion, which does not exist in our example. This is the jump part. So now assume that the drift, so A, this is the integrated drift, sorry. So it's the integral form. So this means the derivative A is x to minus x to 9. Assume that it is dissipative with some power, some order kappa larger than 1. In our case, it is 9. Assume that the jumps are heavy tails are integrated with some power. In our case, it's everything up to 1. So B, well, we forget about B at the moment, so this is Gaussian part. And then there is a theorem which tells you that the moments of the solution exist up to the order p plus kappa minus 1. And this order of so this order of integrability is sharp. You can give counterexamples if you are beyond, so then you're in a bad situation. So this means in our case, in our example, p is arbitrarily close to 1, so this Cauchy. Kappa is 1, so this means you get 1 is essentially 1 plus 9 minus 1, it's 9. You can integrate up to 9. So this is what you can expect. And now the question is, can you recover these moments numerically also? Yes?
When you were saying the naive argument, they say, oh, you take this fish
Yeah.
here, and then this diverge. Where's the pitfall of that?
The pitfall, yeah, so I don't have too much time, so...
Yeah, no, so, like, there's an intuition.
No, the pitfall is, so z is not integrable. Well, you fix your time t, and then you take expectation of z. Well, you can do this, but actually something bad happens if there is a big jump at this time. And this, but the jumps are distributed. So you never have a big jump at the prescribed time. So this means you can think the jump occurred, but a bit before. So, and after that, you had no jumps. And if you had a jump before, then you have a very strong drift, which drives you back to 0. So this is another naive argument, which explains why the first naive argument is not correct. Good. So now I want to make simulations, but of course, in order to do things, I need a benchmark. So, because I just do not want to give you numbers. What is a benchmark? In this example, and this is a very happy situation. If you have this SDE with symmetric Cauchy noise and monomial drift. So this is a very, very seldom situation, rare situation, when you can calculate the invariant density of the solution explicitly. So there are almost no such examples, but in this case you can do this. And this is the formula. So you can just write it. So this is the invariant distribution of this for this equation. It looks like this. You can plot it. Interestingly, it's bimodal, but it's another effect which appears here. And these are the moments. So this will be our reference numbers. So the moments of the order 1/2, 1, 2. This is the energy. So 4, 6, 8, and you diverge at 9 as predicted. So now, simulations. So if you do simulations, and there are actually physicists who do this already. So Ulrike, sorry, but for 30 years, people do simulations of such equations. What do? Of course, you write down the Euler scheme. So Euler scheme, and then you run it. And to be honest, the Euler scheme is not really bad. So because the Euler scheme, so this is a meta theorem. You cannot really find it in the literature, but it says that the Euler scheme converges always. The question is, in what sense? And the Euler scheme, you can rather easily show that it converges uniformly in time in probability. So this is my scheme on discrete time. So you take uniform in time. So the so-called UCP converges, uniformly in time and probability. It converges. So there's no problem. So the question, so how to prove this? The proof is very simple. So why it does not converge? Because very big drift, very heavy tails. Let's cut off the drift. Let's cut off the heavy tails. Then you get localized equation, which is just usual. So then any theorem from any book shows that a localized equation converges. And then since you have dissipativity, you can show that the localized equation lives in some ball, does not leave the ball, and it leaves the ball if something bad happens. and then you increase the ball, so and something bad happens on the event of small probability, and this is exactly convergence in probability. So this is the theory. What happens if you do this practically? And practically, we know that the solution blows up. It explodes. And you see it immediately if you run the code. So this is a typical noise. And you see here, so the noise increments, and you have large values. And this is a solution. And if the noise makes a large outburst, so then we have immediately in 3 steps or 5 steps, we have the so-called sign alternating divergence. And this is, well, so this is some naive explanation why this happens, but essentially, if you go, this is not a stochastic problem, it's a deterministic problem. You can solve exactly the same deterministic ODE if you start at the wrong place, so far enough from 0, and your time step is not small enough, then you diverge. So this is a known problem. So the question is, what happens if you still do this, and physicists still do this? Well, what do we expect? So, and these are simulations. So what you want is, you want to do Monte Carlo. You want to recover the second moment. And this is what happens. I start here at 0, and I simulate 1 million Monte Carlo trajectories independently. So in order to get, to take the sum, so to take the average. Yeah? And some of them, so I integrate, and some of them explode and do not exist any longer. Explode, explode, explode. So, and this is the plot. This is the plot. So if I take, for example, in the good situation, I take h to 10 to minus 5, which is a small step really, yeah? So then if I integrate, so this is this line, I integrate up to time 10. From my 1 million trajectories, I have 1/4. So this means they just vanish. And finally, if you integrate further to 20, you have almost nothing. If you integrate to 30, so this means first you integrate, so then you lose trajectories. So something stays there, but yeah, you get less and less. And the question is, why should it converge to the true value? Of course, it does not. So you just cannot take 1 million, so this sum, because it does not exist. But so people know this, and if you program in Python, for example, so people are aware, this is the so-called ANA problem, not a number problem. And of course, what people do, you ignore this. So practically, you just have, you can take, so a function, say mean, you can put a flag ignore n, roughly speaking, and then you get the so-called, well, it has a name actually, so it has available case moments. So this means you calculate moments from what you get, from what we have. You can do this, of course, and these are the simulations. So these are our benchmark values. And you see here, well, you converge. So this is the moment of the order 1/2. This is the moment of the order 1, moment of the order 2. Of course, all moments exist. It's clear. So because those which do not exist, so we just threw them away. But finally, so what does it mean? If you work only with solutions which did not explore until time t, so this means they are essentially bounded. So because if they are take a large values, they explode. So they are bounded and they are in certain interval. So this means if you calculate the moment, so you have no heavy tails. So you forget about the moments and you get what you see here. You have convergence, but the values are really underestimated. So this is underestimation because of this explosions. And of course, you have to take into account here you start with 1 million paths. At time 10, you have just 500,000 paths. If you calculate further and further, at some point you run out of paths to make simulations. So, well-known problem. Also applies to the Gaussian systems. So absolutely the same, but everything in the Gaussian case will be just exponentially rare. So you have large deviations effects. And here you have, it's well pronounced. People are aware of this, and even in the Gaussian case, but to be honest, I was very surprised, because if you simulate, you see it immediately, but it was, the first paper was by Hutzenthaler, Jensen, and Kloeden, you know, Kloeden-Platten. So look, so in 2012, they published a paper, so 2 papers or 3 papers, where they show that the Euler scheme as it is, it diverges. so in the sense of moments, and they suggested the so-called tamed Euler scheme, which is widely used now for Gaussian systems. Essentially what you do, you cut off large values of the drift. So this is exactly, so you have x to 9, and you divide by x to 9 to h. So this looks like this now. So this is the drift. So at some large value, so you just make it bounded. And if you have bounded drift, you have no problem with explosions. So everything exists. And they proved that for Gaussian systems, you have LP convergence. So for Gaussian, it works very nicely. In the Lévy case, what you see immediately, if you make the drift bounded, you kill the dissipativity. So this means, well, you have no explosion, but dissipativity is lost. And this is what you observe here. So this is the moment of the order 1/2. This is below the integrability order of the Cauchy noise. And the conjecture is that up to 1, it will give you the good result. And there are papers by some guys from Edinburgh. They showed that this converges in the Lévy case, but they assume that Lévy processes are at least square integrable. So their results are not applicable, but I strongly believe so everything will work up to the integrability of the noise. But if you take, for example, the first moment, so this is a picture. So this is your benchmark, and here you fluctuate somewhere, but it's so around 8. You are totally overestimated. And if you take the second moment, it's not depicted here. It will be, you get values of the order 10,000. So huge. Good. So now I think I explained to you so why you have to do something different. So the usual methods do not work. And then it was our idea, so because motivated by this previous paper, so what we can do is we can do the so-called splitting. So, and the idea of splitting comes back to its analysis. It's the so-called Lie-Trotter type approximations for semigroups. So how do you understand this? So the main idea. So we take our process X, which is drift plus noise. Let us write its generator. And the generator consists of, so it looks like this. So this is the drift part. So this is the noise part. You can write here, so Laplace operator for Gaussian noise. Doesn't matter. So we have two. And then, well, so this means, and then you do the following. So you write the propagator. So this is the semigroup, exponential, operator exponential. Propagator at time t of L. And you can write A plus D. Why not? And then you take some time step H and you split. And the problem is that even in the metric case, the matrix products multiplication is not commutative. You cannot do this, really. But the Lie-Trotter theorem says you cannot do this, but you can do this in the limit. So this is the main idea of Lie-Trotter. If you pass here to the limit, it works. So this means if it works in the limit, then what you do, so you take some small h and hope that you have convergence approximation. This is called Lie-Trotter approximation. What does it mean in our case? In our case, well, you see, so these operators are very easy. So the first one, D, is just noise. So this is the semigroup of the Lévy process. So you take test function f, x plus h, expected value. Yeah, so this is the semigroup. So the semigroup of the drift is even easier. It's just a solution of the ODE. So because it's semigroup generated by transport operator, it transports us along the integral curves of the ODE. Okay, but this is a weak setting, so it's in sense of operators. And what we do, we rewrite this as a strong scheme because we want to have paths. And in the strong scheme, it looks like this. So instead of, so we take, so this is just the increment of the Lévy noise. I start at some x. I make a jump. So first I make a jump. And then I solve this ODE. And in the most favorable situation, you can solve it explicitly, like this. So this is an explicit formula. If you cannot, you have to solve it numerically, so which is a different problem. So, and then I apply this intermediate result. So I apply this flow, deterministic flow, to this intermediate result. So this means I solve it like this. I start at x, I make a jump, and then I make a flow, so I go to 0. I make a jump, I go to 0. I make a jump, I go to 0. And this turns out to be a good scheme. So it does not explode. And what is interesting, so it will pertain all the existing moments of the solution. And this is, so to say, the proof by observation. So, and then I will formulate a theorem. So, but this is the proof of by observation. So what you do here, so these are, well, 1 million Monte Carlo simulations. I integrate up to time t. The time step is h, so 10 to minus 5. So the convergence must not be very fast, to be honest. And what you see here, all moments converge exponentially fast, as it should be, to the benchmark value, except of the last moment, 8th moment. So this is not a mistake. This is a very, very slow convergence. So we have a theoretical explanation for this. The convergence is extremely slow here. To get good convergence, you have to take h of the order 10 to minus 10, to be honest, or maybe 10 to minus 9. So then you get something. So, but then the integration time is 3 days. So, good. So this is, yeah. So now, well, maybe I skip. How much time do I have? 40 minutes or half an hour? Okay, so well, then maybe, yes. Yeah, yes, I can. So it will be online. Yeah, so if this one. Yeah. Ah, the previous one. This one. Yes, yes, sure. So now I have time. So one interesting comment. So you see here in the Lévy trotter. Actually, you can write a plus d or d plus a. So what happens? It happens so that everything breaks down. So it's really, so the order is really important. So you write a different order, and then you have the following. And it's clear why. So the different order will be, I start at x, I solve the deterministic ODE, and then I add noise. And the noise is not integrable. So the increment of the noise is not integrable. So this means, so immediately at the first step, I lose integrability. And that's it. So that's amazing because it's just the same scheme actually. So, but taking it to right step, so breaks everything. So, yes, and these are the reverse splitting simulations. So we strongly believe, so we did not prove this, but that up to order 1, up to the integrability of the Lévy process, you can do things. So we didn't prove this, so both schemes will work. But, well, here, for example, for 1, it still works. And for the second moment, you know, so not every increment is large. So, and the only large increments are practically bad. So, but if you do simulations for a long time, so they come pretty often. And this is the picture. But essentially, well, in probability, it will converge, clearly. Because it converged before, so, and then you add something small, so it converges in probability. So why the H moment are underestimated? To be honest, it's not really interesting. So, and now I go to the general setting, and I explain multi-dimensional example, which is also interesting. So what do we do in the general setting? And it is rather flexible. So we are able to solve numerically the following SDE. You have a drift A, and I have another drift small a, which will be very regular, so to say. So small a plus b Brownian motion plus c dz. So is this a Brownian motion? So this is the Lévy process. And let us denote phi. Phi is the solution of this ODE. And now we do the following scheme. At the intermediate step, so we started somewhere, then in the intermediate step, we just write down the usual classical Euler approximation for the regular part. So I will show you assumptions on the next slide. So this is the regular part. Say A, B are bounded, A, B, C are bounded, and the Lipschitz continues. And after that, so you apply the flow which contracts. So this is the scheme. Actually, rather easy to implement. So the only drawback here, you have to know the function phi. So this is really sort of a problem. The good news is that for most one-dimensional systems of interest, like double well potential, so you can write down the explicit solution. So you don't have to integrate numerically. In multi-dimensional case, yeah, you have to work to do something. So assumptions. So just repeat assumptions. So they are. This irregular drift A is kappa dissipative, with kappa larger than one assumption. The second assumption, these regular functions A, B, C are bounded and Lipschitz continuous. You can ask if you can do them unbounded. You can make B A of linear order. And to be honest, A is not important. A is just for convenience, because if A is linear, say, and Lipschitz continuous, you can put it together with large A, nothing happens. But sometimes it's convenient to split. So A and P, the tails of P are of Z are P integrable for some P. So this means that the P moments exist. Okay, now you have more, and this is a bit subtle thing. In order to prove convergence, so this is just unavoidable, that you have to impose the so-called one-sided Lipschitz continuity condition on the dissipative drift. So this is the condition of this type. So of course, each Lipschitz function, Lipschitz continuous function, is also one-sided Lipschitz continuous, but one-sided Lipschitz continuity is a bit more difficult. The good news is, in dimension 1, I will show you many dimensions later. In dimension 1, one-sided Lipschitz continuity is equivalent to the following. The derivative of A is bounded from above. So, and so do I have? Ah, yes, I have shown. For example, if A of x is minus x to 9, yes? So A prime is minus 9x to 8, less than 0, bounded from above. So that's it. One-sided Lipschitz continuous, it works. In many dimensions, I will show you, it becomes a bit tricky. So then we need, so this condition is rather technical, so but it is everywhere assumed in such models. So this derivative must grow polynomially, but some different order. So here is polynomial of the order h, but it should not be so, just any order kappa. And we need some condition. This is especially important in many dimensions. It shows you somehow, well, how to understand this. What is AX? So this is the Jacobi matrix of the drift. It's a matrix. Then you take each component and calculate the Hesse matrix, so the second order matrix. So one order less. And then they should be somehow ordered in space in the right direction. So this Jacobi matrix must dominate in some case, in some sense, the Hesse matrices. It is necessary to prove convergence. In dimension 1, for example, for polynomial drifts, it works. No problem at all, so because A prime prime is of the order A to 7, and A prime is of the order 8. So it works always. So, yes?
Does it have to be globally in X or just big X here?
It's for big X because we have everything up to a constant. So this notation means you multiply by a constant, yes, and add. Yes, essentially for big, of course, because locally everything is fine. So yeah. Good. So and then the results. Okay. So first we show that the numerical scheme really has moments of the required orders. So this is one, and yes, and this is essentially this is the result. So we have convergence. So this is it. So this is maybe the main result. So for all q's, for all moments up to the order, this critical order t plus kappa minus 1. So we have strong convergence, and we can actually also calculate even the order, theoretical order of convergence. And if you do this, if you put in numbers, you will see that it is really very slow. It will be something like 1 divided by 20, for example. So this means slow convergence is not surprising. Good. So this is the result. Everything works. Now, yes, in the Gaussian case. essentially, the same applies in the Gaussian case, and but to be honest, we have no example of if someone needs this. Of course, in the Gaussian case, you see, well, if you have a potential, so we have a diffusion in the Gaussian case, diffusion in the potential x to 10. So what is the invariant density? The invariant density will be, so mu, it will be e to the power, well, I write just some constant, okay, some constant here, normalizing constant, x, yeah, x to 10. So these are very, very light tails. If you compare with Gaussian tails, so the Gaussian tails are of the type minus x squared. And it turns out that if someone is interested, so our splitting scheme can catch the very, very sub-Gaussian tails of the solution. So we had no example for this, so because people are fine with just LP convergence, but for example, so we have the following result. So you have this usual LP convergence or LR convergence for each R, but you can multiply, so these are weights, certain weights, so, and they're exponentially large. And even if you multiply this small distance by a very large weight, it still converges. So it means, but to be honest, there are some, maybe some applications to Orlich spaces, some Gaussian distributions, no idea. Now, the last thing, so I want to discuss. One-sided Lipschitz continuity. So this is really inevitable. So you have to assume this, otherwise you don't have convergence. Or maybe you have, but you cannot prove. But I think you really have problems there. So, and this is equivalent, so this is the definition. In dimension 1, it's equivalent to this, and in higher dimension, it is equivalent to that. You take the Jacobi matrix, transposed, symmetrize, and it must be bounded from above in this sense by some constant. So. The problem is that if you take any system you want to simulate, Dufing, Van der Pol, Lorentz, Brusselator, SIR, they are not one-sided Lipschitz continuous. And to be honest, it doesn't matter if you simulate a deterministic system or so stochastic or deterministic system, because the problem is the same. For deterministic systems, to prove convergence, you need one-sided Lipschitz continuity. So there are papers by, so I didn't send to you. So old paper by Stewart and Humphreys, and they developed some Runge-Kutta method and so on, but they need this in order to show convergence. And they also say, well, in the end of the paper, take Lorentz 63. Well, it doesn't satisfy, sorry. You have to do something. Good. So, and this is the example. But we found sort of a bit of solution, so to say. Lorentz 84. For Lorentz 63 will be the same. So this is well-known Lorentz 84 model. Dissipativity. Dissipativity, you just show it works. You multiply A times the vector. So this is exactly this. All mixed terms cancel nicely, and you have some constant in the norm. So this is one dissipative. Of course, you cannot add here Cauchy noise, but yes, you can do something. And this is not one-sided Lipschitz continuous. So this is the solution. And usually you prove that something is not one-sided Lipschitz by a counterexample. You just find two directions, x and y, such that it doesn't work. And here, so these are the directions. You take one vector, this one, this is another one. The difference is constant, but the scalar product is unbounded. So then, of course, well, you can think, why is it not one-sided Lipschitz? Probably because it's not sufficiently dissipative. So maybe you should add some more dissipativity. And it was our first idea. So we add this term here. And this is coordinate-wise. It is one-sided Lipschitz, and jointly also one-sided Lipschitz. You can add it here, and you immediately get here n+1 dissipativity, or yes, it's n+1 dissipativity. So this means it works. So epsilon is small enough. It's about large values, essentially. And again, so the same example gives you that it is not one-sided Lipschitz continuous. And then you do the following. So you take a bit different weight function. Now I take here the norm to the power n, so the squared norm times this one, and plus this. So it's a small modification. And then it turns out, so suddenly, that this function is dissipative and one-sided Lipschitz continuous. Here, to show one-sided Lipschitz continuity, you have to work. So really, so to check that condition, which I showed you with Jacobian and so on, and it's some work. But now, so here in this example, we can apply, in the Gaussian case, in any case, we can apply the theory. And this is the simulations. Sorry, we have no benchmark, but you can believe now so that it more or less converges. What is this? So these are empirical second moments of the Lorentz 84 system, modified here a bit, because so driven by three-dimensional Cauchy noise. So three-dimensional Cauchy noise is integrable up to order 1. So we modified here, we took n equals to 1. So this is now 3 dissipative. So this is 3 dissipative. So everything works. And 1 million trajectories. Epsilon is a small number. It can be even done smaller. A is and B are from the literature. So, and the picture here is H is 10 to minus 4 and 10 to minus 5. And this is what you usually do. You calculate empirical, so independently for different time steps. And if they coincide more or less, then you believe the result. And here, well, they're within the line thickness. So they coincide. So this is the second moments of this Cauchy-driven Lorentz system. Of course, we cannot solve this equation analytically. So, and we used some Runge-Kutta, some library. So not every library works. So we tested some, and so it's written in the paper which one we used. So looks plausible, but of course you cannot check. So, but simulations so take about 7 hours. 7 hours. It's a virtual Linux machine. 16 2-core processors, so unlimited memory and so on. So it takes about 7.5 hours to simulate this. Okay, so and there are more examples, but I will not go into. As I say, so in some good one-dimensional cases, you can just write down the solution for phi, and then of course you save a lot of computational power here. So, and yes, so on. And yes, and for example, so this is an example why it makes sense to split large a and small a. For example, large a is something nice like x to 4 derivative, and small a like sine. You cannot solve the system in common, but you can solve it separately. So, and everything is nice. Okay, thank you very much for your attention. So this is some literature, so please.
Any questions for Ilya?
So this backward time you said doesn't work. What was the problem?
With the reverse splitting, well, it works in some sense, but even theoretically. Okay, just wait a second. I'll show you. But this is the same problem with taint, essentially. Where is the reverse splitting? Here. Here. You are interested in this guy here. So, well, now let's take a naive argument. Let's take expectations. So this y, so the phi is dissipative. Y is bounded, always. So this is a bounded thing, and this is Cauchy random variable. So this means the moments of h cannot exist for moments larger than 1. Because the scheme is something bounded plus a non-integrable random variable. So, and if you do the other way around, so first you get something and then you confine. Then it works. So that's exactly the case here. Yeah, it's not this one, but yeah. But if you do this pathwise, well.
This Lee Trotter decomposition where
Yeah.
it looks very much like quantum mechanics,
Yeah,
where you
exactly.
can you go to higher orders in
Yeah.
H, like you get a commutator or something.
Of course. Actually, does not matter. So how many operators you have. So, for example, it is convenient from numerical point of view in this equation to split exactly the linear part, because you can solve it explicitly. I have now a master student who splits so the linear part. It simplifies calculations, but of course it's absolutely the same. And there is this strength method, for example. You can increase the order of convergence. For example, what people do in stochastics, you make deterministically half step, then stochastically step, and then again half step. And then it turns out that you can use some symmetries of the operators, and you get higher order of convergence, of weak convergence. Yes, but essentially any order of operators, any type of splitting, and so on. But be careful about the order. Yeah. Okay, thank you for coming.